We're going to talk about the left ventricle. I'm going to draw out the left ventricle here. And I'm going to draw out the rest of the heart as well, but I'm going to just kind of leave dashes here just to make sure that we kind of focus in on just that one chamber, the left ventricle. And this is, of course, next to the right ventricle. And above both of them, you know, you have the two atria, right? These are the chambers of the heart that are going to kind of hold on to the blood until it's time to refill the ventricles. This is our right atrium and our left atrium. Now, a question that came up to me and might come up to you is, why in the world does the left ventricle never have a rip or tear? I mean, if I look at my genes or anything else, you know, you always get these kind of rips and tears over time. And why is it that you don't get these tears in the left ventricle? I mean, it would be disastrous, of course, because the blood would start gushing out of the left ventricle. But what prevents that from happening? And also, what are the stresses on the left ventricle? I mean, what does it have to deal with exactly? So to think about this, I actually wanted to split it up into two categories. You've got diastole, right? And you've got systole. And diastole, of course, is when you have refilling of the heart. And systole is during kind of the squeezing of the heart. And when I say the heart, I should really be more specific. I mean the squeezing of the left ventricle. Because now I'm going to talk in just the perspective of the left ventricle. Now, diastole, what is happening there? Well, blood is really refilling that left ventricle. And so the volume of that chamber is going up, up, up. And during systole, pressure is going up, up, up. So these are the two major issues, right? Now, of course, you have volume in systole, and of course, you have some pressure in diastole. That's not what I'm saying. But what I am trying to get to is the idea that the major issue in diastole is the fact that you've got a full heart. It's especially by the end of diastole, you should have a full left ventricle, the fullest it's going to be. And in systole, the highest pressures that the left ventricle is going to see. So keeping this idea in mind, let's actually now go back about 200 years to someone who thought about a very similar situation around kind of the stress of the wall and what pressure and volume will do to that. So this guy, I'm going to draw up his picture, bring it up. This guy is a French mathematician, and his name was Laplace, and we actually still honor him by kind of talking about his formulas today. And Laplace was a brilliant mathematician. He actually gave a lot of thought to shapes, and the shape that we're going to be kind of focusing on today is the sphere or a ball. So you can just think of a ball like a baseball. I'm drawing it kind of orange, like a basketball, I suppose. And this ball is essentially a hollow sphere, right? And I'm going to draw on the side, actually let me write that sphere here. I'm going to draw on the side a left ventricle, or kind of my image of a left ventricle, right? Something like that. It actually starts looking quite similar to the sphere. So the idea is that Laplace, thought about spheres, but a lot of the ideas he put forward actually apply beautifully to the left ventricle as well. So you've got something like this, where you can see the obvious similarities. Now Laplace thought about this in terms of what would happen if you actually cut away part of that sphere. And let's say you could actually now kind of look down at the cross section of it. Something like that. So he actually thought about it in those terms. And of course I said that this is a hollow ball, so you've got to fill it in. You've got something like an inner circle, I suppose. Like that, right? In fact, let me draw it on the side here so you can make it really nice and easy to see. I don't want you to have to try to figure out what it is I'm drawing. Something like that, right? This is our cross section of the ball or the sphere. And you could do the exact same thing with the left ventricle. Now, the first thing that Laplace thought about was volume. He knew that volume is going to put some sort of stress on the wall. And volume, we know, equals, you can actually write the formula at 4/3 pi r cubed. So if you actually take away some of these numbers, 4/3 and pi, I mean, these are just numbers, right? You can get rid of those. Then you could say, well, there's a relationship or a proportion between volume and radius. And you can actually write proportion as this symbol, right? That means proportional to. And so you can take the cube root of both sides. You could just say, okay, what's the cube root of this side and the cube root of this side? And you could say, well, that means that radius, because that cancels, right? Radius is proportional to the cube root of V, or volume. And on our two pictures, let me just write it on this picture actually, just to be clear, this would be our radius. So this is our radius. Now a second point, I'm just going to first label our picture and then you'll see how it all kind of comes together, is pressure. And pressure is a little simpler to imagine. We know that that's just, you know, a force divided by an area. And here I can draw little blue arrows to signify the pressure on the walls of this left ventricle. This is our pressure. I say left ventricle or sphere, kind of interchangeably, I guess, right at the moment. And third is the wall itself, right? The wall thickness. How thick is the wall? And that's obviously going to affect how much stress the wall feels. So wall thickness would be kind of this quantity, and I'll write W for wall thickness. Now, putting it all together, Laplace came up with this. He said, well, the stress of the wall, we'll call it wall stress, is equal to some of these other factors. He said it's equal to pressure, let me write that first, pressure times the radius divided by 2 times the wall thickness, 2 times W. So that was the relationship. And if you think about it, you get some interesting kind of ideas from this. You say, well, okay, radius, what is that? Well, radius is like a length, right? You're going to measure that out like, you know, centimeters or millimeters. And wall thickness is also a length, right? So you've got very similar, you've got millimeters or centimeters. And we just got through saying pressure is just force divided by an area. So what units are wall stress? Well, length cancels length. So all you're left with is force over area. So really wall stress, and this is pretty cool, is in units of pressure. So it's kind of a pressure, isn't it? But that might make you feel kind of puzzled because you think, well, wait a second. What is wall stress exactly? You might have thought that wall stress was the stress on a wall. Maybe it was something like this. But actually it's not, right? Because that would then just be the P, the pressure that we had in the first place. So then what is wall stress? What would it look like? Well, wall stress you can imagine as this. The stress is we said it's a pressure. Think of the pressure, the pulling pressure. That's kind of how I think of it. Pulling pressure. Literally, the pressure that's pulling apart the wall. So in our first question, when I opened up the video, I said, you know, what is keeping our wall from just having rips and tears? And the wall stress is literally the force, or I shouldn't say force, the force divided by area, the pressure that's going to cause those rips and tears. So you can see that in a way we should have some rips and tears in our left ventricular wall, but we don't. Why don't we? So these, in that little white box, I'm going to draw for you what's inside there. And you know it's going to be little heart cells, right? So little heart cells are lining this wall. And you've got thousands of them, of course, right? Thousands of little heart cells going every which way. And you've got them crossing and going over and under each other, something like this. So what happens is that you literally have thousands of heart cells and they're attached to each other. And these little attachments are, I'm going to draw in white, called desmosomes. So desmosomes are one of the reasons why your heart doesn't just rip apart. You've got these tiny little desmosomes, and their job is to keep everything kind of tidy and tucked. They want to keep the heart cells attached. And that means if they're going to be attached, that they're not getting ripped apart. So these white little arrows are literally counteracting those purple pulling pressure arrows. So this is how you can think about wall stress and why it is that our heart doesn't just rip apart. Lastly, I want to point out that the pressure is actually going to be in our equation, but we don't really have volume in our equation. We have radius. And the relationship is a cube root, right? So if you have a cube root here, but pressure is direct, then that means that between the two of them, volume versus pressure, pressure has a bigger influence on wall stress than volume does. So that's one interesting point. Another interesting point is that wall thickness, which is right here, makes perfect sense, because if you have more and more of these heart cells, that means you have more and more desmosomes that are going to counteract the effects of pressure and radius in this equation.